we will continue our discussions on the flame types in atomic absorption spectrometry. We were discussing about the flow burners. There are basically two types. One is turbulent flow burner, another is premix burner. So, in the turbulent flow burner, the characteristic of that type is that the fuel gas and the mixture combustion gas as well as the sample are introduced only at the tip of the burner. That means, they come from different sources, put into a uniform cone and then releasing simultaneously at the tip of the burner. So, the characteristic of this is it is a combination of nebulizer as well as a burner, because it has to break down the sample also into very small droplets for further reactions to occur, as I have explained in the last class. So, this burner is also known as direct injection burner, because we are introducing the sample also at the entrance of the flame. So, it is converted into a spray also at that point of entry. Several workers have used it for atomic absorption. The turbulent flow burner usually gives a tall narrow flame, which provides a very short light path for the atomic absorption. So, the idea is to introduce everything into the burner and let the burner take care of the atomization, because the sample is also sucked near the end point of the capillary tube and enters the flame. Along with the flame, gas is also entering as well as the oxidizer. So, a typical burner usually consists of a titanium base or a stainless steel base. So, there are other chemically resistant and non-corrosive metals also have been used, but mostly titanium as well as stainless steel burners seem to be of use. They contain either an array of holes or grooves as a slot in order to minimize salt deposition as the underside of the burner surface and also to ensure stable absorption. What we want to do is take the burner, introduce the gas, introduce the sample. So, here we are, they are all burning, and we draw a flame coming out through the flame through a number of slots. Otherwise, what happens? You are having a flame like this, and this provides a very small optical path, only this much. The distance would be hardly 1 centimeter. So, this we do not want to happen. So, what we would like to do is take the burner and then put it through a titanium metal block in which so many holes are made, and then through the holes there will be flame coming out like this. So, this will provide the optical path of the order of about 5 centimeter. If we do not do this, we have a burner going just like a candle burner, the width of the burner would be hardly 1 centimeter, and compared to this the optical path would be less, and sensitivity also would be 5 times less in the turbulent burner. So, a typical burner we have to make it like this, and the actual design of the burner is like this. Here we are introducing primary air, and then there is the hydrogen, possibility for introduction of hydrogen and acetylene, and the fuel also would enter like this, and pilot air. If we are using air as an oxidizer, we are going to mix all of this material which is at the edge is made of titanium here as well as outside. So, this is a typical turbulent flow burner. So, how we increase the sensitivity is utilizing the height of the flame to achieve the long light path, and hence greatly improved sensitivity is to direct the flame into a tube made of suitable heat resistant material. You can also use it as quartz or ceramic. They are also known to withstand very high temperatures of the order of about 3000 degree centigrade. So, this long tube technique is likely to be used for those metals which do not form oxides in the flame. If they form oxides, they will not ionize. So, that is very important in the analysis of oxides, oxide forming elements. If you have oxide forming elements and if you want to analyze them, then you should use a smaller flame like here in this what I have shown you here. So, we will get back to that. The sensitivities of the order of about 10 to 100 times are obtainable through an ordinary flame. These sensitivities have been reported for cadmium, zinc, and even some of the noble metals. So, it is very important for us to decide which type of burner we use. So, the basic requirement is that the light beam must pass entirely through the flame. So, the light beam should be very narrow is another condition to allow the use of the flame burning at long narrow slot, which will give highest sensitivity. The need for the monochromator to accept sufficient height of the flame to give a satisfactory signal to noise ratio usually means that a light beam of finite width is required. So, how do we increase the light beam of finite width is through take a titanium metal block with number of holes. So, that we have a flame which is having an optical path of about 5 to 10 centimeter. And then the turbulent flow burner, it gives a flame which is tall and narrow. While it is ideal for atomic absorption, it provides a much shorter light path and hence exhibits poorer sensitivity compared to a laminar flow burner. The uptake of solution by the turbulent flow burner is also usually less than that of the laminar flow system, and since all the aspirated solution is put into the flame or it enters the flame, it should be more efficient producer of atoms than the laminar flow systems. But there is a small problem. The problem is when you introduce the sample as a liquid, most probably 99% of the systems are introduced only as aqueous solutions. So, the introduction of aqueous solution as a spray into a flame lowers the flame temperature, and this should not happen. That is why turbulent flow burners are not so convenient, and it is also not possible to make the turbulent flow burner into a laminar flow system unless you have one more attachment of the type what I had explained to you about the titanium and steel burner, stainless steel burner. However, there is evidence that some of the aspirated liquid in the total consumption burner passes through the flame without being fully vaporized also. If the light path is very small, very narrow, that means much of the sample may pass through because it is a very fast system, burning system. So, the liquid without getting atomized, it may go out of the system also, thereby reducing the sensitivity. So, these are some of the problems with turbulent flow burner, but otherwise premix flow burner is very ideal. It is available as a routine component in almost all the commercial atomic absorption instruments. Now, let us move on to optical components, and the AAS, as we see, should also have some sort of optical components to direct the radiation from the source and to select the source radiation and then to pass through the radiation, etc. Therefore, AAS covers UV visible wavelength range, that is the range which we need in atomic absorption spectrometers, because most of the atomic absorption lines, resonance lines of most of the elements fall in the UV visible range. So, we need the UV visible range optics also. It is necessary to employ proven monochromators in atomic absorption, since atoms are capable of absorbing radiation within a very narrow frequency interval, and these frequency intervals are of the order of 0.002 to 0.02 nanometers, and the sources are found to be weak if we consider the interval of the radiation frequency. So, for this reason it is not possible to use continuous radiation sources. So, what do we do? I have explained to you this earlier. Some authors recommend that the radiation source used for the atomic absorption measurement should also emit the spectrum of the element to be determined. It will also have a resonance line. With such an arrangement, only we need to separate the resonance lines and others from other spectral lines of the same element by means of a monochromator. So, what is the job of the monochromator? It is to separate the resonance line, that is all. So, you need not have a monochromator before the flame, because you are getting only one radiation from the that is resonance radiation from the source. So, once we separate it, other radiations coming from the flame are usually separated by the monochromator. That is simple. So, if you take a look at this figure, what we have here? We have a source, we have a small filter, and then optics, and then it goes through a monochromator, then absorption, and these are the This is the hollow cathode lamp. From the hollow cathode lamp you are getting number of lines, spectrum lines like this 1, 2, 3, 4, 5, this is the resonance line and these are non-resonance lines. Now, this first part what I am showing you here is the emission line, and in the flame the atoms are produced and atomic absorption occurs. Since we are using only this radiation, we do not need these radiations. So, we need a monochromator for blocking these radiations to enter, and then we need a monochromator to block these also radiations also. This we can set it through a monochromator. Now, what happens? Only this is the emission line and this is the absorption. So, the emission line gets attenuated by the amount of absorption that is taking place here in the flame. So, emission line intensity would be decreasing in this case, that is atomic absorption. So, this is the mechanism. The spectrum of the element under the study is emitted from the HCl. This we have already seen when we have been discussing about the hollow cathode lamps. So, in the flame a portion of the resonance line corresponding to the concentration of the element is absorbed. Lines that do not occur in the absorption are not attenuated. What we mean by attenuation is to reduce the intensity. So, lines after dispersion of the radiation in a monochromator, the resonance lines are again separated by the exit slit. We need an exit slit also, and all other lines do not pass through the exit slit because we are allowing only the resonance line to pass through the flame. One of the greatest advantages of atomic absorption spectrometry, namely its specificity. That means, one element, one technique, and the response from other elements for the same under the same conditions is almost 0. That is what we call specificity. That is the beauty as well as the attraction of atomic absorption. You want to determine any element, you should simply choose atomic absorption, because any other element will not interfere in the process of the measurement. So, the specificity of atomic absorption is based on the use of specific radiation source that emits the spectrum of the element, that is hollow cathode lamp. And the ability of the AAS to differentiate between different elements is solely again dependent upon the half intensity widths. This we have discussed number of times, and of the emission line, that gets half intensity widths we are getting due to Doppler effect, isotope effect, hyperfine effect and several other things, and that ranges from 0.002 to 0.005 nanometer. This range lies beyond the scope of any known resolving power of a normal monochromator. We have seen when we had discussed in the spectrophotometers also, the best resolution you could get is of the order of about 0.2 nanometer, but here what we need is 0.002 to 0.005 nanometers. So, the idea is hollow cathode lamp must be used as a source of radiation, and the monochromator has the most important task of separating the resonance line of the analyte element from other emission lines of the source. If slit widths are large in atomic absorption, what happens? The sensitivity goes down. So, you will not be able to determine the element at lower levels. That is what the atomic absorption or the quality of analysis is all about. What we want to say is, you go down the concentration level, so that you can determine parts per million, parts per billion, parts per trillion and femtogram levels and etcetera. And if we use the slit widths, large slit widths, then what happens? Other radiations will be entering. They are all sort of spectral impurities. So, the sensitivity of the non-resolved multiplets result in several resonance lines passing through the exit slit. So, the sensitivity goes down. So, it is observed that for a number of elements, a spectral bandpass width of 0.2 nanometer is necessary to obtain good sensitivity. The requirement is of the order of please go through the last slide. What I showed you is the requirement is from 0.002 to 0.005 nanometer requirement of the spectral separation, and the instrumental requirement is about 0.2 nanometers. It is necessary to obtain good sensitivity and linearity also of the analytical curve. For other elements, the resonance line is more or less separated, so that larger slit widths can be used without any disadvantage. So, you should not be worrying that if the requirement is only 0.002 to 0.005 nanometers, if I use 0.2 nanometer slit width, the other radiation lines may be coming in. So, the sensitivity may go down, but this does not happen, because the it is other elements, resonance lines are more or less well separated than 0.2 nanometers. That is why you will not be losing much of the sensitivity if you use 0.2 nanometers. In some instruments, you will see that there are people are using, they give you a choice to operate at 0.5 nanometers as well as 0.7 nanometer slit widths. So, that is also possible, but 0.2 nanometers is fairly sufficient to obtain fairly good analytical curves. For other elements, the resonance line is more or less well separated, so that larger slit widths also can be used without disadvantage. This is the reason why they offer you 0.5, 0.7 nanometers. Usually, in most of the commercial instruments, 0.2 and 0.7 are normally provided, and instruments nowadays, the modern instruments offer you a choice of slit widths in a continuous manner. You can choose 0.2, 0.8, 0.5, 0.4, 0.7 like that. You can set the computer to do that job. So, I want to show you a figure subsequently shortly, the influence of the spectral bandpass width on the sensitivity, and the signal to noise ratio also I want to show you, as well as the curvature of the analytical curve, to prove that if you use higher slit widths, the sensitivity will not get affected in atomic absorption to a great extent. So, I have chosen silica as the resonance as the element of interest, and silica has got spectral lines between 250 and 253 nanometers. With such a sufficiently small slit width, every resonance line gives a linear analytical curve within the observed range. Now, you can appreciate between 250 and 253 nanometers, there are several lines for silica. For each of this silica, for each of this analytical resonance line, what I do is I had taken a small sample, and using this wavelength I am going to determine the elements and draw a calibration curve. And when I do this calibration curve, you will see that there is not much difference. For example, this slide will show you lines 250.69 and 251.43 is another resonance line, and 257.61 this is the resonance line of highest sensitivity. You can see that the peak is very high here, and then there are other lines like 251.92, 252.4 this one, and the last one is 252.85. So, I have so many resonance lines to prove the point that you can determine atomic absorption using all these resonance lines. I draw a calibration curve. This is concentration in milligrams per liter and this is absorbance. So, you can see that if I use 251.61, that is corresponding to the highest sensitivity, this resonance line, if I draw a calibration curve, you see that absorbance is a straight line corresponding to concentration in milligrams per liter. Similarly, at 250.69 this one and 252.85 is the next one, like that you will get slightly reduced absorbances, but the beauty is you can choose any of these wavelengths to determine the calibration curve. For example, the absorption in this case in 251.61 is about twice compared to absorption at 251.43. It is slightly more than 250.69 etc., but the point what I am trying to prove is you can choose any of these resonance lines and you can determine the concentration. The calibration does not get affected, but the detection limits will definitely change, but not much also, because the monochromator will allow all these radiations between 0.002 to 0.005 or 0.2 nanometers. You can see that all these are 0.6, 0.69, 0.85, 0.43, 0.41 and 0.92. So, if you choose 251.61 plus or minus 0.2, that is 0.43 as well as 0.85, all these lines will be permitted through the monochromator, and you will end up with an absorption curve somewhere in between these two, in between this and this, because many other resonance lines are also coming in this range. Now, the signal to noise ratio is also optimum at a spectral band pass of 0.2 nanometer. This clearly decreases on both sides as shown in this figure. You can see here this signal 0.02 nanometer signal, this thing, you are going to end up with very high signal, and the 0.07 is fairly broad, and signal to noise ratio is here it is 25, that is lowest, and if you keep on increasing you will end up with 60, 160, 150, 110 like that, different signal to noise ratios. So, the two requirements are placed on the monochromator of an atomic absorption. Firstly, a spectral line, spectral band pass width of 0.2 nanometer is required, and secondly, the entrance slit should have as wide a geometric width as possible. That means, the mechanically it should allow as wide as possible radiation to pass through. However, the entrance slit and exit slit of the monochromator must have the same mechanical dimensions, that is, entrance slit must form an image on the exit slit. So, if both of them, entrance slit as well as the exit slit, if they have the same dimensions, that is a requirement in most of the atomic absorption spectrometers. So, in AAS the image of the radiation source must fall on the entrance slit, then only the image of the same thing will fall on the exit slit. So, we need to have slightly bigger entrance slit. It can also be seen from the figure that the geometric width of the this is the entrance slit with 3 mm and 0.3 mm and 1 mm. So, I have these are the images of the radiation source in the entrance slit. This is what I am talking about right now. So, the with 3 mm it is like this, 0.3 mm, this is 0.3 middle one, and the outside one is 1 mm and the exterior most is 3 mm. So, the image of the entrance slit is also very important. So, what I wanted to convey to you at this stage is it can be seen from the figure, the next figure which I have already shown you, that from the figure that geometric width of the entrance slit, it determines the amount of radiation that falls on the exit slit, and subsequently on the dispersing element like prisms and gratings, etc., and subsequently onto the detector also. So, this means that the noise always accompanying the signal is relatively small compared to the signal itself. The signal is large, noise is always small, and at the same time lower amplification can be employed, so that the contribution to the noise are reduced. That is the most important thing in atomic absorption. We have to have a very high signal to noise ratio. So, the noise we need not amplify to the same extent as the signal, so long as we keep it below a particular level. For the analyst who does not understand much of electrical part, that is lock-in amplification and things like that, low noise means a stable signal. That is what you should understand. If it is a low noise signal, that means it is a stable signal. Therefore, good precision is possible, because the signal will not vary much, and if the noise is very low, signal is very high, the detection limit also would be still lower. That is what we are looking for in most of the analytical techniques what we have been using. So, this is the figure which I had shown you. I hope it is very fairly clear to you now that the entrance slit should be as small as possible, and the exit slit should be same as entrance slit. So, if it is 0.3, you get a very sharp picture, very high signal to noise ratio. If it is 1 mm, you will get a fairly bigger this entrance slit image, and if it is 3 mm, you would get a still bigger this thing, but the signal to noise ratio also would be affected adversely. So, now we move on to the prisms as well as and gratings in the atomic absorption spectrometry. They serve the job of the prisms and gratings is to disperse the radiation into individual wavelengths. This we have seen right from our discussion from the optics of the spectrophotometers onwards. In almost every instrument we have been discussing prisms and gratings. The repeated discussion only helps to clarify the points. Actually, I am not introducing any special points here in the optics, because most of the optical components what we have discussed earlier, they are all coming in the current discussion. Therefore, it is only sort of recapitulation of what we have already learned. So, this is not something new what I am teaching, but we have already discussed and we know about it. Just for the sake of completion of our discussion on the atomic absorption, we are going to say the following things, that the prisms and gratings serve to disperse the radiation into individual wavelengths, and prism based monochromators are basically wavelength dependent. They are wavelength dependent at a fixed geometric slit width. In gratings, monochromators are dependent on the grating constants, number of lines, rulings, grating angle, blazing angle, and the holographic gratings, etc. The quality of the gratings as well as the quality of the selection of the wavelength improve as the number of lines passing through a grating increases. This we have already discussed. So, the two most important mountings, this also we have discussed, are the simple litro monochromator as well as a modified Journey-Turner system. And to refresh your memory, I want to show you the next slide. That is, we have a plane diffraction grating and this is litro monochromator. We have an entrance exit slit here, and this is litro mounting. And if we go to Journey-Turner mounting, it is again a fairly simple arrangement. We have slits here, one slit here, one slit here, and a plane grating is placed in front of them, and then concave mirrors are there. So, that radiation coming through this slit will go on to the concave mirror, reach the grating, and then again go back to another mirror, and it comes back through the exit slit. Very simple arrangement. Both these arrangements are useful for the atomic absorption spectrometer. Both of them are used. Depends upon the model. So, when you are buying an instrument, you should be aware of the litro mounting advantages as well as Journey-Turner mounting advantages. So, you should look for what are the types of optics in a atomic absorption instrument, what you are buying, how many you should get the technical specifications and compare what are the exit slits, what are the entrance slits, what are the optics, what are the whether it is prism based or whether it is diffraction based, and whether they are litro mounting as well as whether it is a Journey-Turner mounting. So, in this connection I must mention to you here that filter photometers cannot be employed in atomic absorption spectrometry because of the requirement of 0.0022 to 0.005 nanometer of the radiation to be separated. Filter photometers can never be able to do that job, is not it? So, since the required resolution itself cannot be obtained, leading to the difficulties, therefore, filter photometers are out of question in atomic absorption. So, the optical requirements for atomic absorption are fairly simple. From the flame, the radiation is passed through mirrors and then lenses, and it may be a combination of the two also, mirrors or lenses, and mirrors and lenses, either way. So, focusing the radiation from the flame to the monochromator in atomic absorption is also very simple, because so long as you focus the radiation onto the entrance slit, your job is done. So, focusing is also very simple, because all you got to do is position the hollow cathode lamp, the filament will be there, they take the radiation and then put an entrance slit for the instrument, where the radiation from the hollow cathode lamp placed outside on the other side of the entrance slit passes through the image. So, from the material standpoint, you can use quartz lenses or silica lenses, both are required because UV transmission characteristics are always there. For example, most of the lines what we have been discussing in atomic absorption, they are all in the UV range, except alkali metals which are in the visible range. So, the optics, if you use glass, you are automatically going to cut off all the radiations coming from the hollow cathode lamp. If you use glass prisms, they will all be cut off because they are not transparent. If you use quartz, they are transparent to UV as well as they are transparent to visible radiation. So, both quartz and fused silica lenses are required because of UV transmission characteristics. Now, spectral band selection. So, again we are coming back to the same discussion, but what I want to tell you now is the term monochromator is in reality a misnomer. Monochromatic radiation, actually it means the radiation with only one wavelength. All spectral band selection devices pass a band of wavelengths that may be larger or smaller according to the quality of the device. That means, whatever monochromator, whatever you use, it will never give you a wavelength of single radiation because of the Doppler effect, hyperfine effect, isotope effect, Voigt profile, Lorentz profile and so many other profiles. You will never get a single wavelength radiation from any of the devices known to us so far. So, the basic requirement of a wavelength selector itself is defeated, because if you are looking for a single wavelength radiation of high intensity, you will be disappointed. So, what is required is you take a slightly increased band of radiation and pass it through the optics to separate the desired resonance line from other lines emitted by the sharp line source. That happens because all hollow cathode lamps are made of the element which we want to determine. So, there are well separated spectral lines. If any background radiation is also emitted by the source, then a curved calibration graph is required, you will be getting. For example, in the previous slide what I had shown you, here these are all very straight line curves, but if you use a band of wavelengths, you will get a curved calibration curves. In this case, you are getting straight line because all are resonance lines, but if you use a band of radiation with which are not, in which all the radiations are not resonance wavelengths, then you would end up with a curved calibration curve which is not linear. But you can minimize this curvature by using a narrow pass monochromator. All the time you are going to get curved calibration curve, but you can minimize it by passing through the narrow pass monochromator to reduce the propagation of the unabsorbed light. That is what I have put here in this slide. The last word is very important for us to understand. The propagation of unabsorbed light must be minimized, then the calibration curve would be linear. What happens with alkali metals? a simple glass or gelatin filter itself is more than sufficient, because most of the emission lines are in the visible range. For other metals, you can use interference filters fairly satisfactorily, but sets of filters with selected cutoffs are commercially available. You can use them as pre-filters and then go on to prisms and gratings, etc. So, the commonest and most versatile wavelength selector is again and again and again, it is the monochromator, which can be said to pass any wavelength between 200 to 900 nanometer, similar to an ordinary spectrophotometer. So, the requirement is a pre-filter and a monochromator, and the job of the monochromator is to select only the radiation that is made of resonance lines, and you cannot use ordinary filters, but you are forced to use prisms and gratings, and the arrangement should be Littrow or Journey-Turner. These two are the most simple as well as useful components of all atomic absorption spectrometers. Now, let us talk about the detection system. A detection system usually includes the detector, associated power supplies, amplifier and readout devices. So, what do we mean? A detection system must include a detector, associated power supplies as well as an amplifier, and it must give you a readout system. All these put together is a detection system, but the detector is always a photomultiplier tube. Usually in almost all atomic absorption instruments, photomultiplier tubes are used, and we have discussed about photomultiplier tubes earlier. I suggest that you refresh yourself if you do not remember about the photomultiplier tubes, and I will not go into the details because of the requirement that I would like to teach you much more. The readout devices usually include, along with the photomultiplier tubes, the analog meters, digital meters you can use, or a simple strip chart recorders. Nowadays, most of these strip chart recorders are out of fashion. However, today computers are incorporated in almost all atomic absorption instruments except least expensive bottom of the line instruments. So, what I would like you to remember in this slide is to look through the requirements for the detection system, that most of the detection systems have got to be a set of electronics along with the photomultiplier tubes. So, the detectors intensity of the job of the detector, that is PMT, photomultiplier tube, is to measure the intensity of the resonance line, monochromator resonance line emitted by the monochromator, and without the sample in the flame by the photoelectric detector. Once you have to measure without the sample, once you have to measure with the sample. When you measure without the sample, you are getting a blank or a reference reading, and if you are measuring with the sample, then you are getting a sample reading. So, a photomultiplier tube is essential if the best results are to be achieved in the determination of metals. However, for general use, it is desirable to modulate the output of the light source using either a chopper or supplying through an AC or DC modulated electric supply. and you have to feed the detector output to an AC amplifier, which is rectified before being fed into the meter. So, in this way any signal caused by the continuous emission of the flame is rejected. Why? Because we are cutting the incoming radiation through a chopper, a mechanical, and what is continuous is always not attenuated. So, it is rejected. So, this is the advantage of a chopper as well as a rectifier. However, any fluctuation in the flame may give rise to appreciable AC component, and it is best to tune the amplifier fairly closely to the modulation frequency of the light source. What we mean is the modulator should be locked to measure only one particular wavelength frequency, so that any fluctuation in the, because flame also can be treated as a substance which will give you radiations of many molecules, like there is carbon, there is hydrogen, there is acetylene, there is water, there could be organic solvents and several other things. So, since the flame is also giving you radiations, it is better to lock in the frequency of modulation to a particular value, so that we measure only at the resonance wavelength. So, in single beam instruments, the accuracy of absorption in the measurement is limited by fluctuation and also drift in the light source. Therefore, a double beam technique is always preferable in atomic absorption spectrometer. Please, if you want to buy a good atomic absorption spectrophotometer, look through the specifications and ask for a double beam instrument. It is always preferable, always you will be comfortable. In such instruments, what happens? The light from hollow cathode lamp is split into a sample beam modulated at a frequency, let us say f, which is passed through the flame, and the reference beam is modulated at a frequency of 2f, that is twice the frequency, which is passed through an equivalent of air path. Same radiation, one is modulated at f, another is modulated at 2f, and the when you are modulating the reference beam, it must pass through an equivalent air path also, that means without the flame. So, just behind the flame this arrangement is made. So, the reference beam passes not through the flame, just backside of the flame, and which is passed through an equivalent air path. The two beams are combined at the entrance slit of the monochromator again, and the photomultiplier output is fed into an amplifier. That is a very simple system, and the amplifier signals from the two beams are separated and the ratio is recorded on the pen recorder or fed to the computer. The demand for routine analysis of large number of samples has led to the development of digital readout and printouts, whose output can be read directly in concentration units, not in absorption units. Nowadays, whenever you want to buy an instrument, normal operation is you take your sample, make a calibration curve, and then fire your sample, and then you want to measure you are measuring the absorbance. Let the computer do the concentration calculation also. That is the advantage of computers. So, most of the instruments are geared to address this requirement, and the output can be directly read in concentration units. Such units are available when used in conjunction with automatic sampling device, so that instrument can work unattended for considerable period of time. So, the photomultiplier tube has the ability to reduce the radiation into an electrical signal with very high gain of the order of about 10⁻⁶, and then fluctuations in atom cells dominate the noise in the systems. So, if the atom cells are more, then the fluctuation will be more. If the production is not stable, uniform, etc., there will always be fluctuations. The short noise associated with the PMTs is basically not so significant, it is insignificant noise, but the spectral responses for modern PMTs exhibit very good sensitivity throughout the UV visible range. So, till date no other detectors have been used in commercial instruments. So, the readout elements, if you have a computer, the most common type of amplifier also can be computerized, and the electronics used in AAS should be is through a lock-in amplifier. This device, as I have explained to you already, locks in at a particular modulation frequency, and therefore, it does not respond to signals from other frequencies, thereby eliminating the noise from the flame. The radiation source is modulated and then that is synchronized with the lock-in amplifier, that is important, and this means that only signals of interest are amplified and the signal to noise ratio will be improved. The amplified signals can then be fed into strip chart recorder or meter for evaluation. In more modern instruments, what we do is we convert it into a digital signal and feed it to a computer for evaluation. We will stop our discussion here, and then we will discuss about the role of computers in the next class, and continue our discussion on atomic absorption, because there are lots of things to learn in this, and we will study about other aspects of atomic absorption techniques.